Welcome back. So the last time we proved the implicit function theorem in two variables, and we stated its most general version, and today we'll prove the implicit function theorem, and I'll give you a couple of examples to illustrate its applicability. Okay. So the last time I stated it in its full detail. Rather than stating it again, let me give you the basic idea of the assumptions made. So basically you have a function, a vector valued function if you will, right, and then it's a CR function, and you solve this, you already have a solution of this. The assumption made is this matrix is invertible. What does this mean? This matrix is the derivative of the first component of f with respect to the y variables, and there are m of these y variables. Recall that this is an Rm, this is an Rn, so there are m y variables and n x variables. And this is the second component with respect to y1 at the point a comma b, of course, and so on. So this is an m by m matrix, and you want this to be invertible. If this is the case, then locally you can solve for this if and only if y is g of x, where g is a CR function. This is what we want to prove. Now, as before, we want to use the inverse function theorem. So as before, consider x comma y, which is in u tilde in Rn cross Rm. Let's call this h. Okay. The first, we simply increase the number of equations by adding trivial equations. Now, if you take the derivative matrix of h at the point a comma b, what will you get? What's the derivative matrix? The gradient of the first component, which is 1, 0, 0. The gradient of the second component, 0. Gradient of the third component, 0. So on. At some point, you'll start taking gradients of this. So it's that df1 by dx1 at the point a comma b, df2 by df1 by dx2, and the x variables run out. Then you take df1 by dy1, df1 by dy2, and so on. Likewise, you take df2 by dx1, df2 by dx2, then you take df2 by dy2, and so on. Okay. So if I were to write it in a more concise manner, this is the identity matrix of the type n cross n. Then you have a 0 matrix, then you have some random matrix, and you have the derivative of f with respect to y, this matrix. Okay. So this is an n plus m cross n plus m matrix. This is an m by m matrix. This is an n by n matrix. The rest are self-explanatory, right? This is actually invertible. This is the crucial observation. And how can we prove that this is invertible, right? So the one way to do it is by using determinants. You can actually compute the determinant of this matrix by expanding along the first row, for example, and using mathematical induction. But I don't want to use determinants to prove this. So how do you prove a matrix is invertible? One way is to show that the columns are columns form a linearly independent set of vectors, right? What are the columns of this matrix? So the columns of this matrix, so once again let me write down what this matrix is. Its identity 0 something and this. Maybe I'll write it here. What are the columns of this? So what do we mean by saying the columns are linearly independent? And this is something star star, I don't care what this is. C1 times this, C2 times 0 1 0 0 0 0 and blah something. C3 times 0 0 1 0 0 0 and something else, etc. There are this n of these C's, and this is whatever it is. The n plus 1th onwards, you'll have zeros all the way until this. Here, what will you have? You'll have df1 dy1 at the point a comma b, df2 dy1 at the point a comma b. In other words, it's the first column of this matrix. Likewise, Cn plus 2 0 0 0 and then the second column of this matrix and so on. If this is 0, what can you conclude? Notice all of these are zeros. So they don't contribute when you're looking at the first n components of this vector. All that contribute are these. And notice that looking at the first n components, we can immediately conclude C1 is 0, C2 is 0, so C3 is 0 and so on, right? Because C1, the vector you get is simply C1, C2, C3, so on till Cn and a bunch of other things, right? So C1 is 0, C2 is 0 and so on until this. So now the rest of these things, they add up to give you zeros here. They already give you zeros in the top, they must give you zeros in the bottom. What does that mean? You are taking a linear combination of the columns of this matrix and you're getting 0. So that means these are all 0 too. Why? Because this by assumption is an invertible matrix. So all of its columns are linearly independent. Okay. So in other words, this matrix is invertible. How does that help? If this matrix is invertible, then happily enough the inverse function theorem carries over and we can say that, notice that h of AB equals a comma c, right? By the inverse function theorem, there exist, you can choose these connected neighborhoods u and v such that connected neighborhoods of A and B, u cross v is in u tilde and W which contains A comma B, A comma C, okay, such that H from U cross V to W is a CR diffeomorphism. Okay, so why is this said by the inverse function theorem says that if the derivative of H at this point is invertible, then H is a local CR diffeomorphism, which means there's a neighborhood of this and a neighborhood of this such that H takes that neighborhood to this neighborhood in a CR diffeomorphic manner, meaning this is 1-to-1 onto and the inverse is also CR, right? Why can I choose this neighborhood to be of this specific type? Well, there is some neighborhood, which means surely there exist two connected neighborhoods u and v around A comma B, so that this happens by definition almost of a neighborhood of a point, and H of uv is an open set. Why is H of uv an open set? Because H inverse is a continuous function. Okay, so I have deliberately not written down why inverse function theorem implies this particular statement. I've just said it in words here. I invite you to please write it yourselves. Okay, write a rigorous statement of this yourselves. Okay, all right. So how does this help? Which means H inverse from W to U cross V, H inverse of, let's call these P vector and Q vector. Okay, this is in Rn plus M, right? Equals, let's say, X vector and Y vector, which is equal to H1 of P comma Q and H2 of P comma Q. This is CR. Okay, this is what the inverse function theorem implies, right? Okay, so what does that mean? And H of H1 of P comma Q, H2 of P comma Q equals P comma Q. That is H1 of P comma Q is P, H2 of P comma Q is Q, right? I mean, H2 of P comma Q is not Q, sorry, this is not true, but H1 of P comma P is P. Why? Because what is H? This is simply X comma F of X comma Y. So H1 is the same as P. F of H1 of P comma Q, maybe let's call this F vector if you wish, and H2 of P comma Q equals Q, right? So in other words, all you have to do is to consider small enough neighborhoods such that of A, which is contained in U, B, which is contained in V, C, right, such that A cross C is contained in this open set and B is contained in H2 of A cross C. Okay. So if we choose small enough neighborhood so that this happens, right, then f of x comma y equals c if and only if y equals g of x. That is what this is saying. Basically, we have solved this, right? This is x if you wish, which is the same as p. This is y, right? So f of x comma y equals, maybe if you want, this is c, if and only if y equals h2 of p comma c, p is the same as x. So y is equal to g of x is basically h2 of x comma c. You're fixing c. That's why it's a function of x. So in fact, this proves, so we are done, QED. So this proves that not only can you solve for y in terms of x in a CR manner, but also actually you can solve for y in terms of x and c in a CR manner, okay? Just like the usual two-variable implicit function theorem. And this g is unique because the inverse, namely this one, is unique. Inverses, if they exist, they're unique, right? So the bottom line is we have simply used the inverse function theorem with more. We have a bunch of equations, we add some trivial equations to them, use the inverse function theorem as a black box, then solve for some of these variables in terms of the others. Okay. Right. So this is the proof of the implicit function theorem. Note that the implicit function theorem, there is nothing special about these, what we have assumed is that if the derivative with respect to the last few variables is invertible, then you can solve for the last few variables in terms of the first few ones. But there's nothing very special or sacrosanct about these last few variables. The same proof shows something more general. That is, if you have a function from Rm plus n to Rm, and if you have any m variables such that the derivative with respect to that m variables is invertible, then those m variables can be solved for in terms of the other n variables in a nice CR manner. Okay? That's what the implicit function theorem is secretly stating. Okay? So the proof of the implicit function theorem shows this stronger statement, if you will. Okay? Right, so the proof can be a bit confusing. It is just taking the two variable case to its logical conclusion. Although there seems to be more bookkeeping involved, the primary ideas are there in the two variable case. Okay, so this is just a more painful version of that. But I hope at least the statement of the inverse function theorem is transparent by now. Okay, we will do a few examples and a few non-examples where it is applicable and where it is not applicable, okay, so that we are all on the same page. So suppose I take f of x comma y, let's say from R2 to R, given by this. Now this is a polynomial, so this is a smooth function. Okay, what do we want to do? We want to solve this. Okay, want to solve this near the point 0 comma 0, because f of 0 comma 0 is 0. We want to solve for this in terms of that, right? Now, so if I take the derivative of f at 0, 0, what's this? This is 2x, which is 0. Derivative with respect to y at 0, 0 is minus 3y square, which is 0, right? So in other words, this 0, 0 is problematic for the implicit function theorem. Why is it problematic for the implicit function theorem? Well, what would the implicit function theorem state? If the partial derivative of f with respect to one of the variables at the origin is non-zero, then you can solve for that variable in terms of the other one. That's what it would say. However, in this case, the partial derivative with respect to both variables is 0. So the implicit function theorem cannot be applied to say that you can locally solve for one of the variables in a nice, smooth manner in terms of the others. Of course, that by itself doesn't mean anything, right? Just because the implicit function theorem is not applicable doesn't mean that the conclusion cannot hold, right? The implicit function theorem is not if and only if. It says that if a condition holds, then you can solve for some variables in terms of the others. If that condition does not hold, the implicit function theorem draws no conclusion whatsoever. Okay. However, in this particular case, you can, what is actually going wrong, right? I mean, you want to solve this near the origin. So the trouble is, if you naively solve it like this, right? Unfortunately, near the origin, you'll have two solutions, right? You can't have only one solution. So if you try to solve for y in terms of this, you will have only one solution. The trouble is, this is not differentiable, right? That's the problem. You can solve for x and for y in terms of x in a unique, continuous, nice manner. In fact, even this function is a perfectly valid continuous function. The trouble here is it's not quite smooth, right? I mean, if you look at the graph of the level set, if you put this to 0, you'll get something like this. So if you look at the trouble here is it's not smooth here, not quite smooth, right? It's a cusp. It looks like this. This is a problematic point, really. Okay. So obviously you can't solve for if you fix, sorry, it's not this, this would have been, so if you fix y, you can't solve in terms of x, you can't solve for x in terms of y, right. So if you give me, if you fix y, you'll have two solutions. So this looks more something like this perhaps. If you give me the same value of y, you'll have two solutions for x, right. So you can't solve for x in terms of y. Sorry, the previous picture wasn't correct, but on the other hand, you can solve for y in terms of x, right. In this neighborhood, you can solve for y in terms of x, except the solution is not well behaved. Over here, if you look at the tangent line, it's vertical, its slope is infinite. That's the problem, okay. And indeed, the fact that there is a problem is indicated by the implicit function theorem, but the implicit function theorem doesn't prove that indeed you cannot solve for one of the variables in terms of the others, right. Let's try this. Again, near the origin, want to solve f equals 0. So again, if you take the derivative with respect to x, you will get 0. The derivative with respect to y, there is 0. So the implicit function theorem is not applicable. Is not applicable. Yeah, right. But well, just because it's not applicable doesn't mean we can't actually solve for y in terms of x or x in terms of y, right? Because if you do this, this means y is plus minus x square, right? You can also solve for, you can try to solve for x also, plus minus square root of y, right? The trouble here is, this of course is not differentiable at y equals 0. Here you can solve y equals x square and y equals minus x square are perfectly nice smooth functions. The trouble is it's not unique, right. Trouble here is the solution is not unique, but the solutions do exist, they are both smooth, but they are not unique. So here also there is a problem, okay. Okay, here is an interesting example. Suppose A is a 2 by 2 matrix, okay, so A is some 2 by 2 real matrix. Can we always find a 2 by 2 matrix B so that B square equals A? That is, can we always take a square root of A? Obviously the answer is no, right. Why is it obviously no? Well, I mean it's in a way the answer is obviously no, because so for example if I take A as minus identity, right, it's not, so don't take A as minus identity, just take A as 0 1 minus 1 0, okay. So it's not immediately obvious, but there is no real matrix so that this happens. It's not, I mean, or there could be, but the point is at least it's not obvious, right. For example, if I take A is minus 0 0 1, certainly there is no diagonal matrix which is real so that this happens, right. There is a non-diagonal matrix which does the job, but certainly not diagonal matrix. So in particular, if the eigenvalues are negative, right, there may not exist a solution, okay. However, even if the eigenvalues are positive, they still are not negative, they may still not exist. So suppose you take this. There exists no B such that B square equals A. Okay. In these cases, they may or may not exist. All I am saying is there is no diagonal matrix B so that this happens, real matrix, right. In fact, in this case it turns out there is a non-diagonal matrix that does the job, but here there is no real matrix B so that this happens. In fact, it is not just, even if I allow myself complex numbers, there is still a problem. I invite you to try to prove this yourselves, but one idea is, if there is such a matrix B, B's eigenvalues are 0, 0. These are the eigenvalues of B, and there is something called the Cayley-Hamilton theorem. That states that such a B would have to satisfy B square equals 0. That is the trouble. Why are the eigenvalues of B 0, 0? If indeed if Bx equals lambda x, B square x is lambda square x, which is Ax, right? Which means lambda square is an eigenvalue of A, so lambda square is 0, so lambda is 0. So abstractly there is a theorem which will say that B square must be 0, but it is not 0. But you can also do it without any fancy theorems. The point is, there is no such matrix, even complex matrix, so the answer to this is no. However, that being said, the claim is there exists a neighborhood of the identity such that every matrix in this neighborhood has a square root. This is a fascinating little result, right? So the way you prove it is you consider this function f from R4 to R4. F is obviously smooth, right? Its entries are polynomials which are smooth. What's the derivative of f at the point identity? What is the derivative? The derivative is a linear map. So it takes a matrix and spits out another matrix. What is this? We have already shown that the derivative is this. Recall that we have done this much earlier. So in other words, the derivative is invertible. Why is it invertible? Well, it acts on h and gives you 2h. So if you give me the right hand side, I can just divide by 2 to get back h. Okay. So by means of the inverse function theorem, we are done, right? A square equals b can be solved if b is close to identity, because identity square is identity. As long as you perturb the right hand side a little bit, you can still find an a. And in fact, you can find not only an a, you can find it in a smooth manner. Okay. So that's a very fascinating little result. Right. So here is one more example. So consider a C1 function. Yeah, f from u and Rn to R. Now suppose the gradient of f is not 0 and say f of a is 0. Okay, what does this mean? That df by dxi at the point a is not 0 for some I. Okay, right. Now what we want to do is we want to solve f of x equals, sorry, it's just 0. We want to solve this near x equals a. This is our goal. Now the point is, by the implicit function theorem, by the proof of the implicit function theorem, if you wish, xi is a C1 function, x2, xi minus 1, xi plus 1 for a C1 function near x equals a. So you can actually solve this by the implicit function theorem. You can solve for the ith variable in terms of the other n minus 1 variables in a C1 manner. Of course, I can make this precise, but there is no point. I hope you understand what this phrase means, okay? What this phrase means, yeah? Right. Here is an interesting and important little point for us. The point is, suppose gamma from an interval in R to U is a C1 map such that f of gamma of t is 0 for all t, then the claim is this is 0. And in fact, we can say more than this, but we are out of time right now. So we will continue with this the next time. We'll analyze this example further and do a couple of more examples before we go on to a very interesting topic that may be of interest to people who work in optimization. Okay. Thank you for joining. I'll stop now.